All right. Hello and welcome to the reading group for today. And today I'm going to be presenting a tutorial on post-implementation timing analysis. So what this means is the following. As a tool, VTR is able to take a circuit design and it will do pack, place, and route. And internal to VTR, it has a timing engine called Tatum. Tatum is very fully featured and very, very fast. And it was designed to be integrated into VTR so that the timing analysis can be used as in the objective functions of the placer, the router, the packer, and the user provides an SDC file containing timing constraints, and that gets passed into VTR, which informs the optimization functions to pack, place, and route your circuit. The downside, and I don't want to really call it a downside, Tatum does not support all SDC commands under the sun. It only supports a subset of all SDC files, all SDC commands, and that can be found here under VPR and timing constraints. And this will detail all the timing constraints that VTR has available. So, oops, constraints. And then you can also go to SDC commands to learn more about what these SDC commands really mean. But today I wanted to talk about what if you wanted more support? You wanted to support all SDC commands to perform a more detailed timing analysis. So let me explain what that means. The idea it being that you have real timing constraints that you know from analyzing your circuit very in depth, and you put these into a more complex timing constraint file, and you also have a more complex detailed delay model, and you want to use the placed and routed solution from VTR to perform timing analysis. So after VTR has run, we want to take the netlist that VTR produces and run a tool called OpenSTA. What this will do is it will take the more complex timing constraints and your more detailed delay model, which I'll show off, and it will perform another timing analysis, this time hopefully more detailed, and you can use this information to decide whether it meets timing or not. And this will work in a flow. So the idea being that you as a user would create your circuit, you'd pass it into VTR with simplified timing constraints, as in you'd simplify your constraints to the ones that VTR can handle. You then, after VTR runs, run OpenSTA with your more detailed timing constraints. And then if it doesn't meet timing, you update your Verilog design. Maybe you add an extra register where timing wasn't being met and so on. And you do this process over and over and over again. I'll walk through this in detail, but that is the key motivation for this tutorial and this flow. Does anyone have any questions on what I just described? Cool. So let me walk through how to perform this tutorial. So the first thing I'm going to do is we're going to be using the CLMA benchmark for this tutorial. So let me just make a tutorial. So the tutorial walks through how to make the directory. I've already made the directory right here. And what I'm going to do is copy the CLMA circuit. I can't remember what CLMA is actually doing, but it's a sufficiently large circuit that is quite interesting. And you can see the BLIF file here. It's a little hard to read as a human, but all you really need to see here is that we have these inputs and outputs, a whole bunch of latches on a whole bunch of LUTs. We are going to be putting this onto the K6 frac N10 frac chain architecture. So let me copy that over as well. And this is just a pretty straightforward fracturable LUT architecture. It's a bit much to go into this, but it contains things like LUTs and flip-flops, which is what we're looking for. And we're going to be using this SDC file. So let me just write this, and then I'll walk through what it means. So how this works is we're going to be creating a clock with period 16 nanoseconds, and it's the name of the input from the BLIF file is p clock. We're then going to set the input delay of all of the input ports, which happen to be PI as the prefix. And we're going to say that they're going to have 0 delay relative to the P clock. And then we're going to set the output delay of all the output ports, which have the suffix of p underscore underscore, and we're going to say that their delay is 0. How to read this is saying the input to the Blyth model p clock, just go to this file, which is, I, which is right here. It's kind of in the middle of everything. P clock is going to be a clock that's going to go rise, and then after 8 nanoseconds, it's going to fall. Then after 8 nanoseconds, it's going to rise. And all of these other signals, we're going to assume that they're only going to change at when on the very first rise, and that's the only time. That's what this max delay is trying to say. It says that when this clock first rises, we're going to say that these ones are going to be not changing before that point or after that point. It's just a way of just making sure these have correct timing information.
So so Alex, if you bring that up for a second. So
Mhm.
I guess SDC, its dominant theme is that everything's clocked. So yeah, it's basically assuming there's a register essentially outside the device,
Mhm.
right?
Yeah.
And it's saying so these inputs, which will be the get ports command. So get ports, and actually that's one. I think get ports just gets all the primary inputs and outputs of the design. Is that right?
Get ports in general does. I've kind of changed it so that it will get any port that has the name PI and then something after it.
So what's the definition of a port in SDC? Is it an input or output of the whole design, or it's just like any port to any cell?
I believe it's the input output of the whole design
I guess
on
that
top
makes
of the
sense because
module.
otherwise this is pretty dangerous.
Yes.
Okay, so it gets all the ports starting with PI, and you're basically saying they're they're they have no delay relative to the clock, which means timing analyze them as registers that are clocked by this clock with no delay after the clock edge. So basically, let's say that your data was coming from another chip across the board, and that board had like a 5 nanosecond delay. You
Mhm.
change that max zero to a 5 nanoseconds.
Absolutely correct. Thank you, Vaughn. Yeah, that definitely helps my, sorry for the definition, but thank you. That really helps.
No, no, that's okay. I mean, that's the way I think of it. Of basically, just think of it as you. SDC doesn't really know how to analyze something that doesn't have a clock. So if you have combinational inputs and outputs, the typical way to constrain them is to essentially say, let's set a delay on those inputs and outputs of the design relative to a clock. So now SDC is happy. It's like I know there's a register on the other side of the board essentially.
Absolutely. And I made this SCC file, but of course, if this CLMA Verilog module was part of a bigger project, this might be set to more specific values for certain inputs which you know are coming from farther away on the chip or some that are coming from closer. Here, we're basically assuming that the register that Vaughn's talking about is right pressed against the module, i.e. there's no delay.
Yeah, and the output delay is basically there will be a register that captures the delay from these output ports, and the delay to get to that register you're saying is zero. So it's
Correct.
also like right beside the chip, basically.
That's absolutely correct. So that's how to read these SDC files. It'll be very useful for the SDC file that VTR generates. So next, we're going to run this command. So I'll walk through what this command does while I'm running it, because it will take a few moments to run. I'm just going to run VPR, and it's going to start running in the background. So let's read this. We're going to run VPR on this architecture with the CLMA file that I just talked about using the SDC file that it showed you. And this wasn't required, but I set the routing channel width to 100 just to some specific fixed value. And what we've added that's different than most VPR runs are these 4 commands. Gen post-synthesis netlist is going to tell VPR after it finished routing, generate a Verilog file that contains all of the primitives that VTR is going to be placing and routing and clustering, and the routes between them as modules in Verilog. It's basically a snapshot of VTR's internal representation of the post-placed and routed netlist. And so that's what this is going to do. It's going to generate a Verilog file. The next line right here is going to gen a post-implementation SDC file. So the SCC file that we provided to VTR may be missing some information that VTR is only going to learn after routing is performed. And I'll show you the output SCC file and explain what that means. But just know that VTR will have to modify the SCC file slightly by adding some extra commands. This next one, post-synthesis netlist unconnected inputs ground. This is just personal preference. You can read the CLL, the command line option documentation for more information. What this is saying is in the netlist, there may be primitives with disconnected inputs or disconnected outputs. In this case, we're just setting the inputs. And all I'm saying here is that if an input is disconnected, just ground it to zero. There's other options like raising it to VDD. There are other options like you creating a fake net that doesn't go anywhere, but I chose to set it to zero for simplicity. And then finally, this one's required for timing analysis. This one removes any parameters from the netlist. This same command, gen post synthesis netlist, is used by another tutorial, the post implementation timing simulation, and that one used parameterized Verilog modules. We can't allow that for OpenSTA. OpenSTA is just not able to handle parameterized Verilog modules, so this just makes it so they're not parameterized. And if I'm going too fast, all of this is written in this tutorial and is also found on the documentation. Right now, it should have finished, which it did. That is great news. And what we can see is generated is, first of all, a new Verilog file has been created, which is top-post-synthesis.v. This is the post-implementation netlist. And it's a massive file. So this is a very verbose, you can think of this as a very verbose version of the input netlist, where every single LUT, flip-flop, and most wires are actually written out as Verilog modules. So for a large circuit like this is 292,000 lines of Verilog code. And you can see that all of the LUTs are found here, and LUTs have their LUT masks, they have names, and they have their inputs, and you'll see these zeros here. These inputs may have been or were most likely disconnected, and so we told VTR to just ground them for this post-implementation netlist. And we can see the inputs and outputs coming in and out. And you can find all of the wires, which there are a lot of them. And an interesting thing that VTR inputs into its post-implementation netlist are these special modules called FPGA interconnect. These are wires that are inserted into the netlist, which connect two primitives together. Now, it may seem kind of silly to make something like this. All I'm doing is taking a wire and connecting it to another wire. Isn't that just kind of useless for a netlist? Well, we want to actually annotate the delays of these wires. If you just use regular old Verilog wires, it I don't believe it's possible to annotate the delays onto the wires themselves using, I will explain in a moment, an SDF file, which we use for OpenSTA. So it's important that we're able to create these fake modules that can pretend like they are a wire which has delay annotations on it. And I'll show what that means, but is there any questions on this post-implementation netlist? Cool. So other files that are generated, so we also have a .sdf file. SDF files seem really complicated, but they're really quite simple. All they're saying is, in that Verilog file that I just showed you, there is going to be a file called LUT5. It's a module, and it has this name, LUT NV388, and it's going to have these delays on its inputs to its outputs. So the delay to go from input 0 to the output of this LUT has a minimum value of 174 and a maximum value of 235. And just for full brevity, this is, I think, the rising edge. And I think this is the falling edge, which in this case, they're equal. So this will also make a bit more sense if we look at this D flip-flop, for example. So there's going to be a D flip-flop module. It has this name, and it has a clock to Q delay that's a minimum of 60 picoseconds, I believe, is the unit for this file, and 120 and a max delay of 124 picoseconds. And it has this setup time constraint, which is 66 picoseconds. and this hold time constraint of 37 picoseconds. So all this file is doing is looking at that netlist and annotating the netlist with delays on all of the inputs and outputs, or in other words, or on all the timing edges in the netlist. So we have a timing edge to go from the clock and the queue. And as I talked about earlier, we have these FPGA interconnect modules, which are basically just the delay of the routing wires. How much delay is it to go from this LUT primitive to this, the input of this flip-flop, based on the routing? And this is directly driven by the routing choices that VTR took. So if a route went all the way around the design, it will be one FPGA interconnect module with an annotation for what VPR calculates the delay to be. So this was just a very big deep dive into this SDF file, and I apologize for going very fast on this. We're going to use this file with OpenSTA to annotate the netlist so that OpenSTA can perform a timing analysis on our circuit. Is that clear? Cool. And the last file that's generated, as promised, is that SDC file. So it's right here. You're going to notice that this part right here is the exact same SDC commands that we passed into it originally. This gets copied and pasted. However, we need to add more SDC commands. So this one right here, set propagated clock, in the original SDC files that you provide to VTR, you don't set the clock as being propagated because at this level, before implementation, the routes between the clock and all of the signals has not actually happened yet. So it doesn't make sense to actually set the propagated clock to tell the timing analyzer that this clock will actually have delays on its wires. So, but however, after VTR has done place and route, we can now say that all of the timing edges, all of the routes that go from the clock to the clock ports of the flip-flops will actually have delays along it. So we're going to tell the timing engine to set the propagated delay to that. I'm sorry if that seems this is just to make sure that the timing analysis that OpenSTA performs is the same timing analysis that VTR performs. By any assumptions that VTR makes on the timing analysis will also be translated over into OpenSTA. And one of them just happens to be setting this clock to be propagated. So we've done the VTR side of things. What I just walked through is this one box right here. And we've generated our post-implementation netlist. We've generated annotations for all the delays on the post-implementation netlist. And we also have our SDC file, which we're going to pass into OpenSTA. The last thing that we need is some way of explaining to OpenSTA what do these modules do? So let me show you what I mean. Where am I going? Here we go. And there's a file called primitives.lib. This file is called a Liberty file. This is used by ASICs predominantly to describe the delays and the timing arcs on the primitives of an ASIC. So for example, an AND gate, this file will describe how many inputs that AND gate has. It has two. How many outputs that AND gate has. It has one. And how do delays travel from the inputs to the output? What are the rising edge delays? What are the falling edge delays? It's very complicated, and I made an extremely simplified. Now, as you saw from before, I actually created an SDF file that's going to annotate the delays. So this file, I can actually cheat a little bit and not provide the true delays. And that's what I'm doing here. I'm just saying, okay, the delay is 0. Let's assume the delays are 0 and let the SDF annotations actually act as the delays. Of course, though, if you wanted a very, very accurate timing simulation, you're probably going to want to actually put the real delays that you would get from doing SPICE simulations. So I want to start by explaining just briefly a summary of how to read these files. We're going to say that there's going to be a cell called FPGA interconnect, or a module in our case from our netlist. It has an input pin called data in and an output pin called data out. And for timing purposes, there is a timing arc going from the data in to the data out, and it has these fall, rise, and fall and rise transition delays, which I just set to 0. This tells OpenSTA to be prepared that when it sees that SDF file, there's a timing arc going from the data in to the data out. And OpenSTA will then take our SDF annotations and apply them to the netlist. The FPGA interconnect is a very simple one. It gets much more complicated when we start looking at LUTs. So in this case, we actually want to put the real function of a LUT. Now, this is a for LUT. It's a four input lookup table, and it has a mask. And how we need to describe to OpenSTA how the inputs are going to behave based on how the inputs are going to rise and fall. And then, of course, we also need to provide the timing arcs. So you don't really need to fully understand exactly what this is doing to understand why it works. But all we're trying to do is we need a way for OpenSTA to understand the internals of our primitives so that it can perform an actual timing analysis. How are people doing?
I'm just staring at this for a second.
Yeah, no, it's
All right,
a
so timing section is you're saying, maybe you want to explain to people what UNATE is and like what that related pin is doing.
To be honest, UNAID is something I really struggle with. It was explained to me by Shifan very briefly. It has to do with how the output is affected by the rising or falling edge of the input. And so I just kind of lifted this from another Liberty file.
I
And
mean,
I
I could
should,
explain it if people are interested. So,
I'm
do
sorry.
you want me to explain UNATEness?
Oh, if you know it, please tell me.
Yeah. So I guess going through this, you can see pin. There's an output pin, so it says pin out. Direction is output. You've given the function. Then the timing related pin in. So this is an arc. You're defining
Yes.
essentially edges inside of this cell, which is a four input LUT. So you've said the output has edges, like dependencies on all of the inputs because you made a bus. Timing sense non-unate. Okay, so unateness is something that allows timing analyzers to be less conservative. So
Mhm.
non-unate means that a rising input could produce either a rising or falling output. Positive unate means a rising input can only produce a rising output, and negative unate means a rising input could only produce a falling output.
Mm,
Why is that useful? It's useful if you have different rise and fall delays in some of your cells or your interconnect, etc. Because instead of at every cell, when it connects to the next cell, like you're going to be doing path traversals, you have to take, for example, the maximum. You're often interested in the maximum data path delay.
mhm,
So if you had a rising delay of 100 nanoseconds and a falling of 120, you'd have to take the worst of those two for the max delay.
mhm.
If you know that it's unate, you know that a rising input will produce a rising output 100 picoseconds later, and a falling input will produce a falling output 120 picoseconds later. And then you can feed that to the next cell. If
Mm.
that next cell is also unate, but now it turns out that a rising input produces an output in 120 picoseconds and a falling produces a falling in 100 picoseconds, you add those together and you get, no matter what, it's 220.
Mm.
And if you had done the worst case of just taking the max delay on each one of those cells, you would have gotten 240.
I see.
So if everything's non-unate, this buys you nothing because you have to actually do the maximum at every single cell anyway. Because a rising input can produce anything and a falling input can produce anything. But when so you like unate. Positive unate is like an AND gate. Negative unate is like a NAND gate. And it allows you to propagate forward rising and falling edges over multiple gates until you hit like a non-unate one, which essentially you have to take the max now of your rising and your falling and say that's everything, send it to the output.
I see.
Does that make sense?
Yeah, and that actually explains what happens. So I should be clear. You should never write a Liberty file by hand. These are usually built by custom tools that spit this out after doing a lot of spice simulations. Writing this by hand is actually a very bad idea, but I didn't want to do these spice simulations for these fake LUTs that we have for this architecture and for any random architecture. So I wrote this by hand. But I originally put this as positive unate, and I found that the answers were slightly wrong, and not always. It was only on specific timing arcs that it was incorrect. So that actually explains the problem I was running into.
It's
As far
also interesting that it actually is paying attention to the innateness because when you give it the function, it technically should be able to figure it out.
That may have come before the function. The experiment by making this positive unate happened before I actually wrote out the function in its entirety. You can kind of cheat here by just taking the and of all the inputs and having that, and then making this non-unate, and that will technically work. But actually writing out the full function, I found actually is much safer, and the solutions were always correct now. So what we have here is always correct.
Yeah, so if you write the function, it should be able to figure it out whether it's unate or not. Let's have this interesting additional thing of there's this the mask, right? Like the LUT mask, which is not really an input. I mean, it's marked as an input here, but it's like it's constant. It won't
Correct.
actually change. And so that's kind of interesting of like whether the timing analyzer would figure that out if you didn't give it. I mean, you didn't put any dependency edges on it, so it's fine. But
Exactly. There's no
it's
timing arcs. I noticed that. So it's treated as almost like a signal that came in, but it's a solid state signal. So it's either 0, 0, 0, 1, 0, 0, 0, and it's just for time immemorial, it's always been those values, which you can
yeah,
think
you
of
would
as if the FPGA was just programmed.
yeah. It's unclear to me whether if you didn't write the unateness, whether the tool could figure that out from the functionality, because you mask is a bit unusual, right? Where it's like a this sort of a quasi constant value, but static timing analyzers usually don't fully understand. Like, they're not really written to sort of figure that out.
To be
So
honest, we can
maybe it
always
would
try
figure that
this.
out, but maybe it wouldn't.
We could try this. At the end of this tutorial, I'll give it a try and we'll see what happens.
Yeah, so I don't actually know if it would figure it out or not, given that mask is kind of a bit unusual.
It'll be really
It's
fun.
not really unusual, but it's basically if it can't tell what is masked, then it has to assume that the function is non-unate. Because if I just go through and mask can be anything, then this function is for sure non-unate.
Mhm.
So
But yeah, I wrote this file. It's part of the VTR project. Anyone can use it. It contains all of the built-in models from the model library within VTR. So it has LUTs, it has D flip-flops, and anything else you might need. The D flip-flops are a lot more complicated. I'm not going into this for this tutorial, but it is a lot more complicated to describe a LUT in this timing model. And people can feel free to look at this themselves.
one of the things that's in there that I think I know what it is, but you got rise times and you've got fall times,
Mhm.
and then you've got transition times, fall, rise, and uh, fall transition and rise transition. So I
Mhm.
think what you've got here is what's often called a like 4 point delay model.
Yes.
So there's like a delay to the cell, and then there's a slope to. So its output starts changing after a certain amount of time. I think that's what it'll define the fall as, and then it has a certain transition time to fully switch.
Mhm.
And that's done to make the delay slightly more accurate. You can propagate that transition time and the delay to the next cell, and that next cell can have entire lookup tables of here's my output delay and my output transition time based on my input transition time. So
Right.
you basically can use somewhat more complicated delay models if you propagate not just a delay but also a slope.
Right.
And then there are even more complicated delay models that propagate more information than that. So
You're absolutely right. And this is meant to be just very simple because I'm going to be stealing my rise and fall delays from the SDF file. VTR did all the math to figure out exactly what the max and min delays are going to be for the rising and falling edges. And we're just taking that and we're going to apply it to our net list. Now, if you want this to be much more accurate, you wouldn't do this. You would put what Vaughn said, that lookup table of delays, and you put that in here, and then you wouldn't read this from the SDF file. You would recompute it yourself using OpenSTA. But for this demo, I just wanted to get the bare minimum, simplest thing working so that you can perform external timing analysis. Thanks, Vaughn. So that's how you read these Liberty files. They're a bit nasty, but let's assume someone already wrote it for us, which I did. You're welcome. So now we're going to run OpenSTA. OpenSTA is an open source static timing analyzer. It's used for ASICs, and apparently now it can work for FPGAs. So that's great news. We have to kind of cheat a little bit here. Normally, you wouldn't write a Liberty file like this for FPGAs in the manner that I've done it, but we're doing that to basically treat our FPGA post-implementation netlist as if it was an ASIC that we're implementing. So you can download OpenSTA and build it on your locally on your system. It's very easy to do. And I'm going to run this tickle file to actually perform static timing analysis. And I'll break down exactly what this tickle file is doing. This is sdf delays.tickle. And this is all looks all weird because of my system. So let me just fix that. There we go. So what we're going to do, we're going to read that Liberty file that I just showed you. So it's VTR flow primitives.libs. That's the exact Liberty file I just talked about. This is telling OpenSTA what are the primitives it's going to see in the netlist and what are their timing arcs like. Then we're going to read that post-implementation netlist that we've created. That's basically how all the models are connected to each other and how many there are and what inputs connect to where are the inputs to the module and so on. We're then going to tell OpenSTA what is the top level design, which just happens to be top for CLMA. We're then going to read that SDF annotation file, which is going to take all of those SDF annotations that say the delay of this input is this, delay of this output is that, and applies it to the netlist. And then finally, we're going to read our SDC constraints. This is the SDC constraints that VTR generated. These next two lines are going to actually perform a static timing analysis. I'm going to compare this to what Tatum performs, but these lines look more complicated than they actually are. All I'm going to do is report all the setup times, report the 100 lowest slack. Yeah, report the 100 lowest slack paths to 3 decimal places and write it into this report file. And this one, because we're setting the path delay to min, we're going to get the hold time. So we're just going to write 2 reports, a setup and hold time report. And then for fun, I'm just going to have it report the minimum clock period and frequency, just so we can see what that looks like. And then we're going to exit the tickle. We're going to exit OpenSTA. So I'm going to run this command by using the STA. So STA is how you run OpenSTA. And for brevity, this is the version that I'm using. I'm using 2.6.2. And all you have to do is just pass it the tickle file, and it will run OpenSTA. This takes a few moments just because 262,000 lines of Verilog is a lot, but as you can see, it's relatively fast. And it says the clock period is 11.84 nanoseconds, and the Fmax is 84.48 megahertz, I believe. And we can compare this to the result that VTR got. So if we look right here, let's just use standard out. If we look right here, we see that the final critical path delay is 11.84 and 84.5. And this one's saying 11.84 and 84.48. I'll explain why there's a little bit of discrepancy here, but there is. We can also take a look at what Tatum's timing reports. So Tatum spits out its timing reports by doing report underscore timing under dot setup dot report. It just writes these files out. And these are the reports from Tatum, and it's telling us that the critical path delay is going from NI45 to NI32. These are just two different flip-flops, and it has a slack of 4.166. I can now look at the OpenSTA timing setup timing report, the one that we just generated, and we will find that it's going from latch NI45 to latch NI32. These are the same ones that we saw before. And it has a slack of 4.162. There is a slight discrepancy. This is because the netlist that's generated by VTR is a bit pessimistic when it comes to its input and output delays. If you're interested in what that means, I have a big issue on this that we may or may not be looking into, but it's about why there's a bit of pessimism. But the idea is that OpenSTA and Tatum are going to get different answers, but because OpenSTA is more pessimistic, if there is a timing violation, OpenSTA, and if Tatum finds a timing violation, OpenSTA will also find a timing violation. So it's a safe assumption to make. Yeah. So that's how we run OpenSTA using a post-implementation netlist. And you can see that in this case, this is the OpenSTA one. I'm printing the 100 least slack path, which is kind of a lot, but you can imagine you can add even more SDC constraints to try and further constrain your circuit by saying, okay, let's ignore maybe the path between this signal and this signal, which is something that you can't do in VTR presently. So it allows you to do more interesting static timing analysis. Now, for fun, I actually really like the idea that Vaughn had. Let's try to screw with this to see if the non-unateness actually makes a difference. So I'm just going to take a quick look, and we can all just have some fun here. This is top photosynthesis.v. I believe this only has LUT5s in it. Yes, it does. So what I'm going to do is open up the Liberty file that I just showed you guys, primitives.lib. I'm going to go to the LUT5 implementation, which is right here. And I'm going to turn this from non-unate to positive unate. And let's see if that actually causes a difference, because I'm actually not sure. So I'm going to run the tickle command again. It won't crash because I think it's still correct. And we do get a different answer, I think. Was that it's 11.67 and 85.7?
It's a
And
little bit faster,
yeah, it's a little bit faster. So
so which makes
um,
sense.
is that pessimistic or optimistic?
Well, uniqueness helps you, right? Because you can be less pessimistic because you get to add up a bunch of positive, like rising edges and a whole bunch of falling edges, and then you only have to max them at the end.
Mm,
So if you have all unate logic, yeah, you can keep track of your rising and falling edges separately, keep adding them together, and then at the very end say which one is the max when I hit the register.
mm,
And if you're non-unate, you have to do that max between rising and falling at every single stage, which is obviously more unless the rising and falling are exactly the same.
I see. So I think it is correct to make this non-unate, not positive unate.
Yeah, non-unate is always more conservative. And to say it's positive unate, you actually need to know that. A LUT can be positive unate, but it depends on its truth table.
I wonder if maybe it's correct. If that's true, then in that case, because we're providing the truth table here, I wonder if OpenSTA is smart.
It might figure it out. Now, we don't actually mark different positive and negative delays, though, either, like rising and falling edges. So,
True.
like if you had different rising and falling edge delays, then for sure you get a gain. Um, Given that you're not doing that, okay, then it's not entirely clear to me where it got the gain from.
Never
Something
mind.
must be, maybe something in there is unate. I'm not sure.
It'll be
So,
interesting to look into that because that could be another reason why you'd want to use a flow like this because then VTR may not have this unate non-unate stuff because maybe it's a bit too much work to do that during pack, place, and route. But OpenSTA, because we've already packed, placed, and routed the circuit, we can be a bit more accurate, I
yeah,
guess.
it's also just work to code all this stuff. Like a lot of this, you're right. It's carrying a more complicated delay model slows down your timing analyzer, but we could probably carry a moderately more complicated delay model without too much impact because you spend a bunch of time traversing the graph. So if you do a little more work at every node, it's not that bad for a while. But they simply kind of go right out of code. So
And the gains you might find in VTR might be small. For all that extra work, you might get a better critical path delay of like a few percent or so.
yeah, it might not be that big.
So it may not be worth it. So this is kind of to motivate why this flow would exist. It's just instead of forcing Tatum to be the most powerful engine on Earth that can do a million different things, you're able to hand off the more strict timing analysis over to OpenSTA, where this could be your final timing sign off before you send it off. Also, what if it's hot outside and you want to run your FPGA? Now you have a different, now your delay model changes because it's hotter, things might run a bit slower.
You're
Delays
supposed to
change.
take that. You're supposed to take that into consideration. So you're supposed to
Oh,
analyze what you're not supposed to analyze at like your max delay should include like how hot could this chip ever get.
mm,
Uh, so sometimes people don't do that, but that's risky.
mm.
So
So yeah, or another way people do this is they will actually do three flows. They'll run VTR three times, they'll run OpenSTA three times, one at using timing models that are cold temperatures, one with timing models that are at medium temperatures, and one at timing models which are at hot temperatures. I don't think that makes any sense for FPGAs, but it's interesting. That's my something.
I mean, it does make sense. That's a multi-quarter analysis, but you can do that in VTR right now, for example, and you can do it in OpenSTA. Just give it multiple delay models,
Correct. That's
right?
yeah.
Like so, The primary thing is that your whole worst hold problems usually occur at low temperatures and low and high voltages, and your worst setup problems usually occur at high temperatures and low voltages. So,
Hmm.
and then you also can have fast and slow chips. So usually you wind up with at least two corners, a fast corner and a slow corner.
Right. So that is the OpenSTA. This is the post-implementation timing analysis. This isn't reserved to just OpenSTA. Any external timing analyzer that you have, if it can accept a Verilog file, Liberty file, and an SDF file, which a lot can do, you can use this flow. I've just verified it to work on with OpenSTA. Are there any further questions before we conclude?